this new chapter 5 on groups, we didn't really work through the notes as such, rather than instead of just looking at these things called the group axioms here. And we started off an exercise, which was an investigation of a particular group. So I'll give the solution to that exercise in a few moments. So today what we're going to do is look again at the group axioms. Say we're going to define what a group is. So a group is a new mathematical object to most of you. You won't have seen it before, last week at least. We'll look at the group axioms and we'll look at some basic consequences, and then hopefully also see another important example of classes of groups. Okay, so very basically, a group is a very fundamental type of mathematical algebraic object. It concerns a set where you've got what's called a binary operation on the set. Now, a binary operation is any rule or algorithm for taking two elements of the set, combining them and producing a third. Now, you're already exceedingly familiar with these kind of things. Ever since you started school, you've been adding numbers together, multiplying numbers, okay? So those are two important arithmetic binary operations that you can do with numbers, okay? Since starting university, you've been adding vectors together. You've been adding matrices together, multiplying matrices. We've been adding, multiplying functions. A very important operation, we've been composing functions, taking two functions, composing them, and getting a third function, okay? These are all examples of binary operations. So since it's such a deep fundamental idea, it occurs all over mathematics. You see it cropping up again and again. Some kind of rule for taking two types of object, producing a third example of that kind of object. So the idea of group theory is we study those types of situations, okay? So rather than studying particularly numbers or particularly functions or particularly matrices, we study what kind of structure or what kind of facts we can draw out about all of these systems in general. Anywhere you've got a set and a binary operation of the set. What must that look like, or what properties must that have, okay? So when you're talking about groups, without any further qualification, if you're just talking about groups, you're talking about a vast range of things that occur all over the place in mathematics. Now, a group is a bit more particular than just a set with a binary operation on it, because that would take in, you know, vast numbers of things and vast numbers of kind of mathematically uninteresting things, just kind of random ways of defining an operation that didn't relate to any kind of structure in the real world, or notion of what you can do with lengths or sizes in the real world. So very specifically now we'll look at the definition of a group, okay? So the definition of a group amounts to giving four axioms which are properties that the binary operation must have. So a group is a pair of things. It's a set, which we call G here, and a binary operation. It's traditional to use asterisks to represent a general binary operation, okay? But we look at these things, A asterisk B or A star B sometimes is how we read that. You think of that as A plus B or A multiplied by B. But it's here in the axioms, it's just an abstract binary operation, okay? So what are the four axioms, okay? So we talked through these last time. But we'll go through them. We only did so quite quickly last time. The first property is we say the set has to be closed under the operation, so closure. So that simply says that whenever you take two elements A and B from the set in question, G, the binary operation between them, A star B, must also be in the set, okay? So the set is closed with respect to the operation. Performing the operation on elements of the set never takes you outside of the set. It just plays around with the elements that are in the set, okay? So the idea is, you know, you add two integer numbers, you get another integer number. You multiply two real numbers, again, it's another real number. It's that kind of idea. But this must hold for every single pair of elements. So the set must be completely closed with respect to the operation. Now, the remaining three axioms should be familiar kind of facts. These are familiar properties that you're familiar with from thinking about operations on numbers, operations on matrices, vectors, functions, etc. The property number 2 here is the associativity axiom. So this is something which you recognize as true of addition of numbers, multiplication of numbers, addition of matrices, multiplication of matrices, all the operations we do with functions, addition, multiplication, composition, and so on. But if you want to do a triple product, A star, B star, C, well, since star is a binary operation, it's just a rule for taking a pair of elements, the one on the right and the one on the right and the one on the left, combining them to give the third element. When you see a triple product, A star, B star, C, there's two ways you could actually go about evaluating that. Either first evaluate, as the brackets show on the left, first evaluate B star C, and whatever the answer to that is, evaluate A star that answer. Or alternatively, on the right-hand side, as indicated by the brackets, you first do A star B, and then do whatever that element is, star C. Okay? Well, the associative property is that whichever of those two ways you choose to evaluate the triple product ABC, you always get the same answer. Okay? So in order to be called a group, we require that the binary operation satisfies that property. Okay? But it's a property you're familiar with. You use it all the time. You know, anytime you see three numbers on a page to add up, and the person tells you what the answer is, you don't go questioning them, well, which order did you add them up in? Did you add the first two together first, or did you add the second and third together first? You don't need to question them because, you know, it doesn't make any difference. You're free to add up the numbers in any order. Such operations are called associative. Third operation says the third axiom, says there must be a very special element in the set, and this is called the identity element. It's given it's usually called the letter E, which comes from the word eigen in German, I believe, meaning kind of oneness or something to do with selfhood or something. Eigen, like eigenvalue and eigenvector and so on. Anyway, this special element, the identity element E, this is the very special property that when you do E star A or A star E, no matter what A is, you always just get A. Now, you're already intimately familiar with that idea because you know about the number 0 and addition. If you add 0 to any number, it's still, you don't change the other number. So 0 is the identity for the operation of addition on numbers. 1 is the identity for the operation of multiplication with numbers. 1 times any number doesn't change the other number. It's still just whatever it was. The identity matrix, if you're in a situation where you're adding matrices together of a certain, you're adding matrices of the same size together, the appropriate identity element is the 0 matrix of that appropriate size. When you add it to any other matrix, it leaves the other matrix unchanged. And if you're in a binary operation setting where you're multiplying square matrices together, square matrices of a particular size, so you can always multiply them, the appropriate identity element is the identity matrix. It even uses the same word, the identity matrix of that size. When you multiply any matrix by the identity matrix, it doesn't change the matrix. So in order to be called a group, it has to have this property, that there must be this special identity element in the group. And axiom 4 says that the group must have inverses for all of its elements. Now, the inverse of an element A, as you can see here, is the special element A inverse, such that when you multiply it by A on either side, you get back the special element E referred to in axiom 3. So the inverse elements for addition of numbers are the corresponding negative of the original number. So the additive inverse of the integer -2 is the integer +2. Because when you add -2 to +2, you get the identity element 0. So you can think of what the inverse elements are in the various contexts. And as we meet groups in each context, we'll clearly identify the appropriate inverse elements. So in order to be called a group, it must have this structure. So you can kind of think of it as these 4 axioms are the kind of minimal Well, they're not exactly the minimal, but they're a nice set of axioms that will provide a lot of interesting mathematical structure to the object. So it won't allow in things that just have random structure which doesn't relate to anything in the real world. But they're not too prescriptive either. They're still very permissive in that there's a huge range of such things in various different branches of mathematics. Okay, we've already mentioned several of them this morning. Okay, and there are many, many other kinds which we don't have the language to speak about yet. Okay. So group theory, in like one sentence, group theory is just working out what the consequences of those four axioms are. And just exploring and finding out about all the interesting structure that flows, or all the interesting mathematical structure that's possible in sets and operations satisfying just these properties. Okay. So in a moment, you'll see in the next few pages in the notes, there's a few results and lemmas and theorems about groups. So these are just some of the initial extra consequences, or some of the initial properties that all groups have, which we'll go through in a moment. But first of all, I want to come back to what we looked at last week. So last week, as a kind of motivating example, we introduced a new kind of group, which you probably haven't seen as called a group before. So I'll quickly review what this is, and I'll show you the completion of the operation table that we were working with. So this group, so it's not a group of numbers, it's not a group of matrices or that, it's a group of functions. It's a set of 6 functions. Now, what are these functions? Well, they're very mathematically interesting, they're very geometrically interesting functions. The functions are the 6 symmetries of the regular triangle in the plane. So you think of a regular triangle in the plane, a triangle with all sides are the same length, so all the interior angles are the same. Just a nice symmetrical regular triangle. Now this triangle has several symmetries, 6 symmetries, exactly. These are operations that you do to the plane that leave the triangle as a whole the same, leave the triangle appearing the same. Okay, it moves the sides around, it might flip the triangle a bit, but just as a simple 3 lines stuck together, it's still going to remain the same after these operations. Now, what are these operations? Well, of course, you pretty quickly see that you can rotate the triangle in various ways. You can rotate it around its center. Don't worry too much about getting all these notes down because they are up on the Google Hangouts page, on the Google Plus pages in the comments to last week's lecture. You can rotate the triangle in various ways. Now, you can rotate it 1/3 of a turn, or you can rotate it 2/3 of a turn. Those are 2 symmetries of the triangle. They're movements of the whole plane, transformations of the whole plane that leave the triangle unfixed. Now, we also admit into our discussion the rotation by 0 radians. Okay, you can argue that, well, that's not a rotation, you're not rotating it. Well, I'll just argue saying, well, yeah, we are rotating it, but by 0 radians. It's a trivial transformation. It's the trivial function. It's like the identity function on the plane. Just sends every point in the plane to itself. Well, we allow that in and we call that a symmetry. It's the trivial symmetry of the object. Every object has this symmetry. Every object is unchanged when you do nothing to it. But doing nothing is one of our allowable symmetries. And we're calling it E because it is the group identity. The other types of symmetry that it has are reflections. Okay, so there are 3 axes sketched out there, S1, S2, S3, and we'll use the letter S, S1, S2, S3, or whatever, to refer to reflection in that corresponding axis. Okay, so you reflect the plane in this vertical line S1. Okay, so every point on the right of the line gets mapped to its mirror image on the left, and vice versa. Every point on the line remains in the same position. So these are the 6 symmetries that the triangle has. And the operation, the binary operation that we're using here is the operation, very crucial, very deep, fundamental operation you do with functions is you compose them. You run one function after the other. And then there's the key observation that we make here. Because we're talking about symmetries, things that leave the triangle unchanged, when you compose two of them, so you do the first one, the triangle is unchanged. You do the second one, the triangle is still unchanged. So that means when you compose them, run the two together, it leaves the triangle unchanged. So composing two symmetries gives you another symmetry. It's like the closure axiom. You take two of these symmetries, choose any two from the 6, and even choose the same one twice to compose one with itself. You compose the two symmetries, again, you're going to get another symmetry. So this looks like it's going to have group structure. It's a set which is closed under a certain binary operation. And it will satisfy all the other properties as well. Composition of functions is just automatically universally associative. There's nothing special about this particular set of functions, just any kind of composition of functions is automatically an associative operation. There is an identity element, okay? Doing nothing, rotating by 0 radians. If you compose that with any other operation, you've still just got whatever the other operation is. And the presence of the inverse elements will be revealed in a moment. You might already start to put them together in your head, what the inverse of each of these elements is. But we'll see it clearly in a moment, because what we did last week was we started to draw this. Now, this is called the Cayley table. Every group has a Cayley table. And for groups of a reasonable size, as long as they will fit on the page, it's kind of an instructive exercise to do out the Cayley table. The Cayley table is simply the operation table of the group, the multiplication table of the group. Okay, so it's a table. You've got row and column headings. The row and column headings are just all the elements from the group. And we need a convention here is that in the entry in the interior of the table, the convention is outlined down here at the bottom of the page of the visualizer notes. In row A and column B, you put the element A after B, A composed with B like that. And we need that convention to say whether this is going to be A after B or B after A, because we will remember that composition of functions is in general not commutative. Okay? You can't assume that A after B is the same as B after A. It is in certain special cases for special reasons, but typically not. Okay? So that's the entry we're going to put in the interior of the table. So last week we explained, well, the first row and column in the interior of the table are straight away you can put them down because that's composing with the identity on various sides. And the identity doesn't change it. So you're just repeating the row and column labels in the first row and column of the interior of the table. But after that, you have to start to think about things and calculate with things. Okay. Now we showed last time by means of, there's an interesting way that you can figure out what these compositions are by labeling vertices. So we label the vertices 1, 2, 3 at the triangle, like that. We were getting here the composition S1 after R1. So R1 rotates at 1/3 of a turn. It goes to 1, 3, 2, as you can see in the middle triangle. Then we did S1. S1 reflects it in the vertical line, if you look at the previous page of the notes. So that flips the vertices to look like in this final configuration, 1, 3, 2. Now the composition is just the single operation which goes from the beginning point to the end point. So which of it must be one of the 6 symmetries we've already identified. So you stare at it, and you interrogate the vertices, and you see which one is it. Well, it's obviously S2. Okay, because we go from this starting configuration 1, 2, 3, we end up in 3, 2, 1. The vertex 2 has remained where it is, and 1 and 3 have swapped positions. Okay, so that's the reflection S2. You can do a similar thing for all other compositions. Okay, and in the tutorial, we investigated the completion of this table. So we worked out all these products, and suddenly we can see everything that's going on in the group. Okay, we can see all the products, all the compositions in the group. Okay, now I won't go through the whole discussion again, but we discussed various things about this in the tutorials. I'll add this page, this completed page, to the comments on today's lecture, so you can study this and interrogate this afterwards. Okay. Now, we'll say some more about Cayley tables in a moment. There's a section in the notes where we come to them. Okay, so it's just very simply the operation table for the group. For groups of small finite order, as long as you can fit them on the page, you can do these, and it shows you everything that's going on in the group. Okay, so that will go up on the lecture comments afterwards. Now, obviously, there's nothing special about the triangle. We can look at these groups of symmetries for any geometrical figure at all. And the set of all symmetries of a geometrical figure under the operation of composition will always form a group. And the more symmetries the object has, the more interesting the group will be. The more symmetries that will be there, and potentially the richer the structure that the symmetry group can have. Okay, so let's come back and do a bit of abstract group theory, where we're not talking about a particular type of group made of particular named objects under a particular named operation. Now we're going to switch back and do a general theoretical discussion instead for a while. Okay. First of all, we have an extra, well, it's not an extra axiom, because it's not part of the group definition, but already there's a very obvious difference between two different types of groups we have now. Okay. This example of composition of functions, I made the point that composition of functions is not commutative in general. Typically, you compose a pair of functions, it depends on what order you take the functions in. However, the arithmetic operations of addition and multiplication of numbers, it is commutative. You're familiar with the idea that 2 times 3 is the same as 3 times 2. It doesn't make a difference what order you add numbers in or multiply them. Okay? So those are commutative operations. So straight away here, we can divide all groups into one of two camps. There's the groups where the operation is commutative. You can always flip A star B into B star A. And there's the non-commutative groups, the groups where you can't always do that. Okay? So straight away, we have a dichotomy into non-abelian groups and abelian groups. Abelian groups are much easier to understand and much easier to study because they have this very special property that in all the products A star B, it's always equal to B star A. Non-abelian groups are, therefore, harder to study. And there's a much richer, more complicated, more detailed structure to non-abelian groups than there is to abelian groups. In the third year group theory course, which is going to run for the first time in September, essentially, we can completely understand abelian groups. Essentially, there's no more mystery. And we can easily cover all the details of the proof and all the details of the description of exactly what's going on with abelian groups, or finite abelian groups anyway. We can completely discuss that and prove all the details of it in a third-year undergraduate course. By contrast, exactly what's going on and exactly what the rich and complete story is about non-abelian groups is a far harder task and is, an area of active research at the moment. And there's a grand enterprise which you might read up. It's been described in some kind of popular maths works called the classification of finite simple groups. And that was a grand research project stretching many years. It was completed in the late 20th century, I guess, where people set out to completely describe all the, well, simple is a technical term, all the groups, all the kind of groups that were the building blocks of non-abelian groups. And it's a mammoth task, involved many, many mathematicians over like many years. And it's one of these things where to get the full complete story, the full complete proof, it's kind of scattered amongst loads of research publications. It's a big long story. It hasn't even all been condensed to a single book or anything. But let's do some initial abstract group theory ourselves here. and investigate some facts that follow. I've already used this term. We used it last week. The order of a group simply refers to the size of the group, the number of elements in it. Well, first of all, we have this theorem, and it looks kind of strange because in the way I've been talking about groups, I've been talking about the identity element a lot of the time. Well, here we've got a theorem which takes the time and takes the care to prove that the identity element is unique. So if you glance back at the axiom, the identity element axiom, it just says there exists this element E. Now, you should know from your work in logic with Said that if you have a logical statement that says there exists something with a property, it's not saying there exists only one. It could be there could be several elements with this property. And when you look at it initially, there's nothing which immediately tells you that there couldn't be lots of different identity elements. Think back to the simple example of addition with numbers. Okay, 0 is an identity element. Maybe there's some other weird number out there which is different from 0, such that when you add it to any other number, it leaves it unchanged. Now, there isn't. But, you know, the first time you think about it, you think, oh, yeah, maybe there could be. Then you think about addition of numbers a little bit more, and you're saying, well, no, anything with that property has to be 0. But it's certainly not immediately obvious for, say, multiplication of matrices. So you've learned about multiplying square matrices with Stephen. You've learned and you've discovered that there's this special identity matrix, such that when you multiply it by any other matrix, it leaves it unchanged. When you first started looking at that, I probably, if I'd worked on you, I probably could have convinced you that there was another special type of matrix which did that job as well. Such when you multiplied it by any other matrix, it left the other matrix unchanged. I probably could have persuaded you a strange arrangement of zeros and ones, because the definition of matrix multiplication is kind of, it's not too easy to grasp when you first meet it, about multiplying the rows into the columns and summing them and so on. So, you know, maybe there are some strange sets out there which have several identity elements. Well, if they're groups, if they satisfy these 4 properties, they don't, because we can prove it. So this is theorem 5.1. So let's look at its proof. It's a nice proof, just a couple of sentences. And it's, I won't say it's exactly a proof by contradiction, but it's a very nice proof. It's suppose, so it starts off with a sentence, suppose that E and F are 2 identity elements of the group. Now, I don't stress suppose they're 2 different elements. If I'd stress that, then we'd be doing a little proof by contradiction. But I suppose I've got an identity element in this hand and an identity element in this hand, E and F. What the proof does is it shows you that they have to be the same element. Okay? But starting off, potentially, they could be different elements, E and F. And the way it does it very nicely is just to look at the product E star F. Okay? So E and F, if they are 2 identity elements, they're both in the group, so I can operate them. I can apply the binary operation to them, E star F. On both screens. So E star F. Now, what we do is we look at E star F in 2 different ways. The first time we look at it, we say, well, we kind of ignore what F is, and we just say, well, E is an identity element. So E star F has to leave the other element unchanged, so it has to be F. That's the property that identity elements have. So E star F is equal to F. But then we look at it again, and this time we kind of ignore what E is, and we say, well, no, look at this second element, F here, that's an identity element. The property that an identity element has is when you do E star, or when you do X star, the identity element, it just gives you back X again. So E star F also has to be E. However, by this whole thing, this whole setup, E star F is just a single element, because star is a binary operation. It's a rule for combining a pair of elements to give you a third element. So simultaneously, it's F and E. Now, it's a basic, the basic starting point for any kind of rational logical discussion is one thing cannot be two different things at the same time. Okay, so everything has to be itself. So if E star F is equal to F and it's also equal to E, the only possible way that can happen is if E equals F. So the two identity elements I was holding in my two hands at the beginning, in fact, I'm just holding two copies of the same element, two instances of the same element. Okay, so identity elements are unique. So that's our first proof in abstract group theory. It doesn't appear we've done much, but when you think about it in a different way, we've done a huge amount, because producing this argument here, if you think about it, simultaneously, we were talking about addition of numbers on the integers, multiplication of the non-zero real numbers, addition of all 3x3 matrices we were talking about here. We were here talking about the situation of multiplication of all non-singular 2x2 matrices, 3x3 matrices, 4x4 matrices. We were simultaneously talking about every example of a group that there is in mathematics. There's an infinite number of them. They come in many, many different interesting contexts, different areas of mathematics. So what looked fairly innocuous here, it was actually something quite powerful. This argument applies to every single group that there is, every single set and binary operation which satisfies just these four properties. So we were proving a universal fact that all groups have. The identity element in them is unique. Okay? And when you think about, say, the integers under addition or the real numbers under multiplication, the non-zero real numbers, you kind of think, well, yeah, you don't have to prove it. Of course, 1 is the only element that when you multiply it by something else, leaves the something else unchanged. And of course, 0 is the only thing you can add to something to leave the other thing unchanged. But in other more complicated areas like composition of functions or multiplication of matrices, it's not immediately obvious to me that there might be some other kind of identity element out there. Similarly, the next theorem is about inverse elements. The inverse elements are unique as well. Now, the inverse axiom says for every element in the group, every element is paired with some other element, or it could be itself, which is an inverse element for it. So when you do x star this other element, you get back the identity element. This is saying, and again, it's not contained in the axiom. The axiom doesn't say it's unique. All it says is there exists an element A inverse with this kind of property. But who's to say that there couldn't be more than one? Again, think back to like multiplication of large square matrices. You're familiar with the idea now, because you've worked with them a while, that inverse matrices are unique. Any matrix, if it has an inverse matrix, it is unique. However, when you first met matrices and matrix multiplication, again, if I got you at the right moment, I probably could have convinced you or persuaded you that there might be some matrix which has two different inverses. Yeah? Two different matrices, so that when you multiply it by these matrices, you in both occasions, you get back the identity matrix. Maybe you would have believed me, maybe not. But it's not immediately obvious. Okay? But it does follow from the four group axioms. So here's another case where we're going to do a little argument, a little proof here, and we're simultaneously talking about every single example of a group that there is. So, and it's an argument in the same spirit as the previous one. So what do? Well, we give ourselves a group, G star, we let that be a group, and we give ourselves a group element, G. And now we do the same trick again. We suppose that there are two inverses for it. We call them F and H. So I'm in a group G, a group large G. I've got a group element little g, and I'm supposing that there are two inverse elements for it. I'm calling them F and H. So these two elements have the property, well, they're both inverses. So G star F is equal to F star G is equal to the identity. That's because F is an inverse to G, and also H is an inverse. So G star H is equal to H star G, and that's equal to the identity element. Now, there's nothing I've said yet which tells you that F must be equal to H. So how do we get to that conclusion? Well, what we do is we look at, in the middle of, so I've got a whole line of equations, several equations here. But look at the middle one. The middle one, we've got an application of the associative law to the group, looking at the product F star G star H. So we put one inverse to the left of G, the other inverse to the right of G, and we look at that triple product, F star G star H. Now, the associative axiom, because that's a product going on in the group, the associative axiom says that it's the same no matter if you, on the left, we evaluate G star H first, on the right, we evaluate F star G first. The associative axiom says that they're the same. But from the middle, if you work out to the edges, so looking at this one, if you step to the left, you see, well, H is an inverse for G. So G star H is equal to E, the identity, but the identity star F has to give you F. So this triple product is equal to F. But then if you use the other version, which is the same as it, F star G, and then star H, well, F star G, F is an inverse to G. So F star G is equal to E, the identity element. But then you're looking at E star H, so that must be equal to H, because E is the identity element. Oh, but hang on a second. Half a minute ago, I said this thing was F. So F and H are the same. It's a whole row of equations. So this follows from doing a neat, appropriate application of the associative law to F star G star H, where F and H are potentially two different identity elements, two different inverse elements of G. But then this neat little argument quickly shows you that, well, in fact, F has to be the same as H. And all we use, the only things we used there were the group axioms. There's no other facts about G that we use there, just the group axioms. So this argument applies to every single example of a group that there is. Okay. There's one more of these arguments, which I'm going to leave you to read through yourself, and this is about a cancellation law. A thing that you use all the time with addition of numbers or multiplication of numbers or similar operations in matrices. Cancellation law, if you have A star C, if you know that that's equal to B star C, you can kind of, informally speaking, cancel the C from both sides to conclude that A is B. Or you can also cancel it if it's on the left. If C star A is equal to C star B, informally, you can strike out the C from both sides and conclude that A is equal to B. So you can do that in any group, and it essentially just relies on the fact of multiplying both sides by the inverse element on the appropriate size. In fact, it's just a one-sentence proof. Okay. I'd like to finish in the 8 minutes I have in defining two new types of group, which I think some of you will be familiar with already, perhaps some of you not. Okay, previous to this, there's a little bit of discussion about number groups. The integers, the rationals, the real numbers under the operations of addition and multiplication. They form groups, except of course for multiplication. Multiplication doesn't form a group on the integers because you have to involve fractions for the multiplicative inverses. And also you have to leave out the special element 0 from the rationals of the real numbers in order to get a group, because 0 doesn't have a multiplicative inverse. There's no real number you can multiply by 0 to give you 1. And don't say infinity, because infinity isn't a real number, and what the hell is infinity times 0 anyway? Who knows? So I'll leave you to read through that. We also have the modular arithmetic groups, which are related groups. And these are very important in number theory, in the study of prime numbers, and in the study of factorization of numbers. So we use these a lot in the second year course number theory and cryptography. Okay, we're focusing on the integers here. So not fractions or anything, just the integers. We're looking at our operations of addition and multiplication, but a special kind of addition and multiplication. We have what's called a modulus n. So n is some fixed number strictly bigger than 1. And then we have these two operations, addition modulo n and multiplication modulo n. So what is that? Well, to do addition modulo n, for integers a and b, their sum modulo m is defined to be the integer c, and the integer c is the smallest non-negative remainder left after you divide a plus b by the modulus n. So we take the integers a and b, you add them in the normal way to get some large integer. You then divide that large integer by n. Divide it by n as many times as you can, and you'll be left with a small remainder. The small remainder will lie greater than or equal to 0, be some integer c greater than or equal to 0, but strictly less than n. So it's the small remainder left after you divide a plus b in the normal sense, after you divide it by n as much as you can. So we take c to be the value to the binary operation, a plus b modulo n. So it's addition modulo n. You can do multiplication modulo n in a very similar way. You take the two integers a and b, you multiply them in the normal way to get a large number, a times b, and you divide that number by n. And after dividing it by n, you're left with a small remainder. The remainder might be 0 if n goes in evenly, or otherwise it's a small number between 0 and strictly less than n. So in that case, that small remainder is the answer to the operation a multiplied by b modulo n. Now, these two operations form groups. So we have two types of groups. So we have Zn. So Zn is the notation for all the possible remainders you can get. 0, 1, 2, 3, up as far as n minus 1. And we use the same symbol plus as we do for the normal operation of addition. Okay, but here it's meaning addition modulo n. This system forms a group. Okay, whatever n is, if n is some fixed modulus strictly greater than 1, fixed integer modulus strictly greater than 1, this set, Zn plus, the set of possible remainders after division by n, under the operation of addition modulo n, this forms a group. We'll have a look at an example of it in a moment. We can also do groups with the multiplication, except at this time, there's an issue of when numbers have inverses. So for instance, consider if the modulus is 5, consider the product 2 times 3. Well, if you multiply 2 and 3 modulo 5, when you multiply 2 and 3, you get 6. You divide it by 5, you're left with a remainder of 1. Okay, so 2 times 3 is equal to 1 modulo 5. So 2 and 3 are inverses of each other. 2 times 3 gives you the identity element 1. If you're doing multiplication modulo 8, 3 is its own inverse. 3 times 3. 3 times 3, of course, in the normal sense is 9, but modulo 8, that's equivalent to 1. If you divide 9 by 8, you get a remainder of 1. So 3 is its own inverse. Elements are allowed to be their own inverses. However, when you come to consider multiplication modulo 8 and you look at 2, what's the inverse to 2 under multiplication modulo 8? Well, let's search for it. 2 times 1 is 2. 2 times 2 is 4. So these are all modulo 8. 2 times 3 is 6. Okay, we're waiting until we get a remainder of 1. 2 times 4 is 8, which is 0. 2 times 5 is 10, which is 2, modulo 8. Should be doing 3 lines here anyway. 2 times 6 is 12, which is 4. 2 times 7 is 14, which is 6. Now, I've failed to find an inverse for 2. I've gone through all the possible remainders, 0, Well, 2 times 0 is 0. I never get an answer 1. I never get a remainder of 1. So 2 does not have an inverse modulo 8 under multiplication modulo 8. Okay? 3 does, and lots of other numbers do. Now, it turns out, and this is something which we explore in detail in the number theory course, there's a very easily understood, or there's a very clear condition which tells you when numbers have inverses under multiplication modulo whatever, modulo n, and when they don't. And this condition is that they must be what's called co-prime to the modulus. So two numbers are co-prime to one another. So co-prime is a property that a pair of numbers have. It's a relation. Two numbers are co-prime if they share no integer factor apart from 1. Everything can be divided by the integer 1, of course. So 1 is always a common factor of any pair of integers. But if it's the only common factor, or minus 1 as well, if there's no other common factor between two integers, we say that they're co-prime. It turns out, and this is something we explore in detail in the number theory course, if two numbers are co-prime, or if the number is co-prime to the modulus, then it will have a multiplicative inverse under multiplication modulo n. If it isn't co-prime, as 2 isn't to 8, you see 2 is not co-prime to 8, because they're both divisible by 2. If it isn't co-prime, then it fails to have a inverse under multiplication modulo n. So what that means is, in order to form a group under multiplication modulo n, we have to kick out some of the remainders. We have to get rid of any remainder which is not co-prime to the modulus. So in set builder notation here is the description of the set Zn times. So this is the set which forms a group under multiplication modulo n. It's the set of every a such that a is between 1 and n, and a is co-prime to n. Okay. So in the tutorials this week, we better finish up there. I'd like you to investigate these groups. These groups under addition modulo n and groups under multiplication modulo n. There's some examples there, example 5.4 to explore. We can do some Cayley tables for them. If you look at question 1 at the end of the chapter, question 1 at the end of the chapter asks you to investigate the Cayley tables for some small examples of these groups.